Okay, hi guys. Not many people here today, but you guys just submitted assignment two. Is there any questions on that before we start the class? Okay, so what we did in the past week was um, we finished the difference and differences chapter, and so the primary focuses in that chapter was basically difference and difference methodology and synthetic control. Okay. So I think I already sent you assignment three. So that will be an assignment based on the previous chapter, and that will be due on June 14th, which I think is the very last day of the class or the semester, and then after that is the exam period. So you guys will be having a final exam, don't forget, and that will be during the exam period. So I don't know the exact date yet. Actually, I don't know if it matters because I think I'm going to give you guys like a 2-day take-home exam, so I might not just I might not listen to whatever day they choose, but we'll see. Um, okay, and also don't forget that the referee report is due on the 5th of June, so in 4 days. Okay, so make sure you guys get that to me. If you have questions, feel free to email me. Normally I'm available in office hours, but obviously, you guys don't have that luxury this semester, so whenever you need me, I'm available through email or we can set up a Zoom meeting. Okay. If there are no questions, I will start the last chapter that we're going to cover. I did want to cover more topics, but um, of course, this semester was a bit shorter. It was only 11 weeks instead of 14, so we just don't get to cover as much topics as I would like. Also, some good news on Wednesday, we're going to have another guest lecture. So that's going to be Vadim Marmer. And he was my professor in my master's. He's probably the smartest economist ever. Like, he's just really great at econometrics. So he's going to be teaching you guys about machine learning and like regression trees, okay? So he's actually going to be doing kind of an interactive class where he's going to have a data set and be working on it in R. So you guys can follow along if you want. So I'll be here and that will be on Wednesday. So not like this week Wednesday. So I'll send out an email. I just need to confirm with him. Okay, so that's basically the next 2 weeks. And yeah, so we have that class on Wednesday and then basically another week of classes and we'll be done. So we're basically near the end of the semester. It feels like it went by really fast. So, I mean, I'm not going to do a formal review class just because you guys have access to all of the recordings on my Google Drive and also on YouTube. So it seems kind of silly to do a full class reviewing when you guys can review at any time. So I'm going to leave that on you. But if you do have any questions on any previous material, you can ask at any time during classes or send an email, okay? But the final exam, you didn't have a midterm, so the final exam is going to include all topics that we've covered, starting from um, like chapter one all the way through this chapter, which is we're going to finish off here, which is regression discontinuity, right? So we have the introduction to impact evaluations, and then we looked at causality and the counterfactual problem. And then we looked at randomization. After randomization, there was instrument variables, and then difference and differences and not event studies and synthetic control. And this final week, we're going to focus on regression discontinuity. So the final exam will cover all of those topics. And just think about the main emphasis of my course, what it's been. So we've talked a lot about methodology and the assumptions needed for causality. So that's a big focus of this class. So expect questions like that. I'm not going to ask you to do any data analysis for the final. It's all going to be written answers. And in the previous semester that I taught, it was more math focused, maybe the final, but since this is an online course and we haven't really been doing much math written out, you've just been seeing my slides. Oh, you have a question? No, you're good. Okay, so it's been more slides and less math heavy, so that will be something similar to the final, okay? So I'll probably ask some sort of long answer question or what methodology would be best suited to a certain case study, okay? So that will basically be the formula for the final exam. So don't, obviously, it's going to be, oh, I have chat, sorry, I just noticed. Can you repeat what you said about the final exam? Oh yeah, okay, so final exam is going to be open book. So I'm going to give you guys like 2 or 3 days to do it. I'll give more specific instructions once I actually make it and figure out. But yeah, you'll have 2 or 3 days to work on it on your own. And it's not going to be math heavy, right? Because we actually haven't done many math problems together. So the previous semester we did do some deriving of formulas, etc. But this semester we haven't really done that since it's been through the computer. It's been mainly conversational, talking about papers and methodology. That will be the main focus of the exam. So I would say there might be multiple choice too, but it will definitely be mostly long answer. So yeah, and it's going to cover all of the topics mentioned so far in the class. So from chapter 1 all the way up to this chapter we're going to start now. And also the guest lectures, possibly. Sorry. So the guest lecture from Siddharth and also from Vadim Marmor, which will be this Wednesday. Oops. Okay, so any questions on the final exam? Okay, so just remember that the final exam is cumulative, and I think it will be worth, I can't quite remember, 30 or 35% of your final grade, so it's quite significant. Also remember that a large part of your grade is this referee report, which is due on the 5th of June. So, is that the Friday? Yeah, that's due on Friday at midnight. Okay, so can I repeat final exam? Okay, someone else just asked for the final exam. I just mentioned it a lot in detail. Basically just that it's going to cover all of the chapters and it's going to be more written, so long answer questions and maybe a few multiple choice as well, but it won't be too math heavy. So you don't need to worry about memorizing any formulas. You're also going to have access to your computer, so there's no sense in memorizing anyways. Okay. And the referee report. So make sure that when you're doing it, if you haven't finished already, I don't want just a summary of the paper, because then I would just read the paper, right? So I want you guys to be critically thinking about whether their methodology is suitable, whether they achieve causality, how their paper can be improved. So I really want you guys to focus on that part of the paper rather than just rewriting their abstract for the whole time, okay? So yeah, if you have problems with your referee report, you can send me an email or we can have a meeting and we can talk about it. If you have problems writing in English, I don't expect perfect grammar, so don't spend too much time worrying about your English being perfect because I'm not going to reduce points for bad English. I just don't care about it. So just make sure that you have the essential points critiquing the paper. But if you are concerned, definitely send me an email before Friday, and the more time the better, because then I have more time to respond. Okay?
I have a question.
Yeah.
So what if The paper I'm reading has a lot of methodologies and a lot of strategies. I mean, should I focus on the main ones or how should I approach it?
Yeah, so what I would do is just focus on the main strategy. They're always going to have like one primary one, which they use to make their estimates. And then oftentimes they'll have some different specifications, like if they add fixed effects or if they look at a different methodology altogether. You can think of those as robustness. So robustness is basically trying to confirm the results you find in your main specification. So you can say, well, this is their methodology and this is their estimates. I'm not too sure about it. Maybe it's biased because of this factor, but they provide X, Y, and Z robustness checks using different specifications, and they find similar estimates. So now I feel more comfortable that they're finding somewhere near causality, or you can do something like that.
Okay, thanks.
No problem. Anything else? Okay, you guys will do great. I believe in you. So let's start this regression discontinuity chapter. Okay, so just a show of hands, who has already covered regression discontinuity in previous courses?
Yes.
Yes?
Yes.
Okay, thanks, Jorge. Okay, so yeah, since you guys already have somewhat of an idea, we're just going to basically go through the framework, the important assumptions, and we'll look at some papers, okay? So regression discontinuity, or RD, research design is an impact evaluation method which is exploiting the exact knowledge of some rule which determines treatment for some program. Okay, so you can think of any type of program is going to need an eligibility requirement, right? So remember back to chapter 1, to have a well-defined program, you need to know exactly who is a beneficiary of the program, so who is going to receive treatment. Well, sometimes these programs are based on this cutoff rule. So basically, for example, if you have some sort of index or continuous variable, and we can say, oh, well, if their characteristic is above this cutoff, then they're eligible for the program. So for example, if you think of the poverty index, which we actually did in assignment 1, right? You guys looked at this program called the HISP, which gave health insurance subsidies to poor households. And they actually decided the households based on an index cutoff. So the index was poverty. So poverty index was from 0 to 100, and 0 was the most poor, and 100 was the least poor. Okay? And so they said anyone with a poverty index score below 58 is eligible for this program. So you can see how this index is a continuous variable, right? So it goes from 0 to 100, and households can take any value within that range. And then the authors or the experimenters randomly choose a value. They say 58 is the number with which below people can access this program and above they cannot. Okay, so this is basically the idea that we're going to use to manipulate the regression discontinuity design. So RD identification is based on the idea that in a highly regulated world, some rules are really arbitrary or random, and therefore they can basically provide good experiments. So remember when we talked about as good as random, when we randomly decide where a cutoff is in a poverty index, like how different are people in households from that have a poverty index score of 55 going to be from 56. probably not super different, right? So the authors are using that randomness to basically use a strategy that's as good as random. So we create randomness from this cutoff rule. So when this rule is random, we can manipulate them as an exogenous channel, which is basically giving us causality. Okay. So regression discontinuity designs come in two styles, fuzzy and sharp. Have you guys heard of the difference between fuzzy and sharp regression discontinuities? Maybe not. Okay, so when you think of a regression discontinuity, you probably think of the sharp design, which is directly looking at the cutoff effect on your outcome variable. And that's when basically we have a sharp discontinuous jump where treatment status is 0 when you're on the wrong side of the cutoff and goes directly to 1 when you're on the correct side. Whereas a fuzzy design is not perfectly determining treatment status. So there might be some people that are non-compliers, right? So there's people that are on the side of the cutoff that might be receiving treatment when they shouldn't be, and some people on the other side of the cutoff that are not receiving treatment when they should be. So there's some non-compliance when we use a fuzzy discontinuity. And remember, when we use or when we have imperfect compliance, what do we need to do? That's a hard question. Let's see who gets it. So remember when we have the randomization. When it's perfect randomization, we can just use an OLS regression to find causality, right? But what do we need to do when we have imperfect compliance? What's our strategy? So that's fine, it was a while ago. So when we have imperfect compliance, remember there are some people that are put in the treatment group that are not receiving treatment, and people in the control group that are receiving treatment, right? So there can be incompliance on both sides. Well, that selection is not random, right? So then we are concerned that there's bias in our estimates. That's when we use an instrument variable strategy. So we're using the intent to treat effect as an instrument variable for the treatment of the treated. Do you guys remember that? Okay, if you don't remember it, definitely go back and review that. But the fuzzy design for regression discontinuity is actually doing something similar, right? Because they're saying that we have a cutoff rule, but not everyone is complying to this rule. There's some people on the side of the cutoff that should be receiving treatment that aren't, and vice versa. Maybe some people on the side that should be controlled that are receiving treatment. So what we need to do then is use an instrument variable setup. Okay, so we'll go through that more later. So regression discontinuity is a useful tool to conduct impact evaluations, specifically on programs. So social programs often use an index to decide who is eligible to enroll and who is not. So like the HISP we just talked about, any anti-poverty programs basically are targeted to poor households, and poor households will often be identified by a poverty score or index. We just talked about that. So poverty score can be based on some sort of formula that measures a set of basic household assets to estimate for income. Okay, so households with low scores are classified as poor, and then higher scores are typically better off. And so anti-poverty programs will have to choose some sort of a value of the index below which people can receive the program. Okay, so for example, Columbia's system for selecting beneficiaries of social spending is one such example. So the program's targeted based on this index called the SISBEN, SISBEN, which is an index for poverty. It's continuous, and the values is determined by household characteristics such as their location, the materials of the home, the services that are available, demographic features, health, education, income, and the occupation. So you guys can think of this like this is all the information that your INAHO data set would contain. So this could be one way to create some sort of index if you don't have access to income, right? So the government established two cutoffs surrounding this index. So children of households with scores below the first cutoff are eligible for completely free education from grades 1 to 11. And then children of households with scores between the first cutoff and the second cutoff are eligible for a 50% subsidy on fees for only grade 10 and 11. And then children from households with scores above cutoff, number 2, are not eligible for any program. So you can see how there's kind of a treatment rule, right? So below the first cutoff, which is the lowest on the poverty index score, so the most poor households are going to get the highest treatment or the highest benefit. And then a second category or group of households will get a little bit of support, but not as much as the most poor group. And then finally, the richest portion of households are not going to get any. So the cutoffs are often considered to be rather objective, like how do you choose like 57 to 58 on the poverty index score? Like it's not going to make a huge difference. So it can be a bit objective or subjective, right? Subjective. So this is a great design for regression discontinuities. So the sharp regression discontinuity design, which I talked about, is what you guys probably think of when you think of regression discontinuity. It's just a very straightforward case. So the sharp regression discontinuity is used when treatment status is deterministic and a discontinuous function of a covariate, so xi. Okay, so an xi would be your running variable is what we call it. And that could be like the poverty index or income or something like that. So for example, our treatment status, remember di equals 1 is if we're treated. We can say di equals 1 when xi is greater or equal to x0. So here we're calling x0 our cutoff. So think of the poverty index example. X0 would be 58 on the poverty index. Well, I guess in this case, it would be less than or equal to 58, right? Because for the poverty indexes, people lower than 58 receive treatment. But this is just an example, so it could be either way. And then di equals 0 if xi is less than the cutoff. Okay, so these are setting up the treatment rules. You know your cutoff, right? This is where the groups will either receive treatment or not, whether they're on the left-hand side or the right-hand side of the cutoff. Okay, so this is a mechanism that is deterministic. See here, deterministic, because once we know the household or individual's xi, we know precisely what their di is. That's what makes this a sharp regression discontinuity design. Is there any questions on that? Okay.
Miss, can you repeat the last thing you said, please?
Yeah, sure. Okay, so the last thing I said about, well, we know that our, whatever the xi is here of the individual or household is going to determine what their treatment status is, their di, because we know what the cutoff is, right? And so once we know their their individual characteristic, we can say whether they're going to be treated or not, just based on their XI. So for example, we know the cutoff is 58. So if a household has their characteristic is at 61, we know that they're going to be treated because 61 is greater than 58. And so with that reasoning, this mechanism of the Sharp regression discontinuity, this is deterministic function because your XI is determining your DI, right? So your household level characteristic is determining your treatment status. Okay, so in this case, we have two cutoffs. Well, okay, so in the example in Colombia, they had two cutoffs for two different treatment groups. But in this one right here that we're looking at, there's just one treatment status. But you could do two different treatment groups as well because you have two distinct cutoffs, right? But yeah, in this example, there's just one cutoff. So additionally, it's a discontinuous function because no matter how close xi gets to x0, treatment is unchanged until xi equals x0. Okay, so this line is really important. This is what makes us use a regression discontinuity and not any other methodology. So we need the setup of the program to be such that everyone up until the cutoff receives treatment, and then there's immediate switch after the xi equals x0. Okay, so an example of a Sharp regression discontinuity, American high school students are awarded some National Merit Scholarship Award. So it's based on a test score, the PSAT, and I think that's like, I don't know, some sort of standardized exam. Oh, it's a test taken by most high school students who intend on going to college. Okay, so we are interested to know if students who win these awards are more likely to finish college than those students who don't. So does this scholarship actually help people finish college is basically the question. What would be the problem of doing an OLS regression for this analysis in measuring the effect of students winning this award on finishing college? What do you think would be the omitted variable bias there?
Intrinsic ability or something like that?
Yeah, absolutely. Like, you think maybe people that are have higher ability will be more likely to win this award and then also more likely to finish university, right? So there's a lot of omitted variable bias if you're just to run an OLS. So that's why using a regression discontinuity design is really essential. So the Sharp regression discontinuity design will compare the college completion rates of students with this test score just above and just below the threshold for winning this scholarship, right? So they're looking at people who just barely won the scholarship compared to people who just barely did it. And they're assuming, okay, well, since this scholarship cutoff rule was pretty random, so say you need like an 80% on the test to get the scholarship. So probably people who get like 80.5% are not that different in characteristic to people who get 79.5%, right? When there's such little standard deviation in the score and the cutoff is decided randomly, you have to assume that the two groups right beside the cutoff will be very similar. And then they use those two groups as the treatment and the control, right? And they're saying, well, this cutoff rule is as good as random. So if we have some sort of continuous variable and we randomly decide to put a cutoff at one point in it, people people on either side of that cutoff are going to be very similar. And that's basically the design strategy of regression discontinuity design. Okay. So yeah, we talked about this bias. In general, we might expect students with higher test scores to be more likely to finish college, which would be the omitted variable bias problem. But this effect can be controlled for by fitting a regression to the relationship between this college completion and the test score within the neighborhood of the award cutoff. So when I say within the neighborhood, it's a really subjective math term. The neighborhood is really never defined, but it's some sufficiently close area to the cutoff. Okay, so just sufficiently close. We don't specify how close. But then later on, that's when bandwidth selection becomes important. So if you guys have heard regression discontinuity, bandwidth selection, that's what that comes from. It's trying to choose a neighborhood around the cutoff that's acceptable to have causality. So we're really looking for basically a distance from the cutoff where the people in the treatment group still look very identical to people in the control group.
I have a question.
Yeah.
So it is like mandatory. I don't know if mandatory, but it's necessary that that your X variable that determines the cutoff, it has to be included in the model, or it can be completely exogenous.
It definitely does have to be included in the model because normally X explains your Y, right? So if you think of this is test score, and if we're looking at the function of test score and explaining the probability of passing college, it is explaining it. So normally we do include it in the regression. I can't think of a case where authors have not. So the standard is definitely to keep the X in your regression, yeah.
I was referring like to the exact grade you get in the SAT, for example. You have to include that in the model, like.
Oh, yeah. So what we're going to do, I'll show you the methodology a bit in a second, but you take the difference from individual I to the cutoff. So their distance from the cutoff is going to help explain.
Oh, okay. You construct a new variable.
Yeah, exactly.
Kind of?
Yeah, exactly.
Okay.
Yeah, so you're just normalizing basically each individual score minus the cutoff, and that will be, I'll show you. So for example, this would be a regression. So you can see here that we're looking at the distance between individual I's test score and the cutoff. And so we have one variable that's going to just be treatment status, that's explaining our outcome variable. And then beta 1 can be the distance between individual I's test score and the cutoff. And then a final, basically, interaction term of the treatment and the distance. So that'll be for each individual I.
Okay, so like this variable is not like intrinsically important, but the distance or the propensity to be close to the cutoff, right?
Yeah, exactly.
Okay.
And then
Thanks.
from there you can choose how much, or basically how much of the sample you want to include. So like how close within to the cutoff. So that would be part of bandwidth selection, which can also be important. But yeah, that's like the standard regression that authors would use.
Thanks.
No problem. Okay, going back. Okay, so back to the test score example. Remember that we're interested in whether achieving this scholarship improves the probability of completing university. So suppose the cutoff to winning the scholarship is at least a test score of 80%. So we can suppose that people who score 79.9% are pretty similar from people who score even like 80% or 80.1%. So then we're using this cutoff as an exogenous source of variation to look at the differences in educational outcomes between people just above and just below the cutoff. So I'm really stressing that we need to only look within the cutoff, because if we use the whole function of our test score outcomes, so think of this, I'll draw it out. Ah, what? Oh, there we go. So this is college, complete college. And this is test score, right? Let's say this is 80. That's our cutoff. But we already know that there's going to be some function or relationship between your test score and whether you complete college, right? So let's say there's some positive function. Except at 80, there's a positive effect of completing college. So we see something like this. Okay. So this is basically the regression discontinuity design, because you see there's some positive relationship between your x and y, but the only part of the causality is going to be some neighborhood around the discontinuous jump. I'm going to call this our window for causality. Causality. Okay. Why do you think this can only be our window for causality? What would happen if we compared all of the individuals over here to all of the individuals over here?
Because then it wouldn't be like, it wouldn't act as a, not exactly as an instrumental variable, but I mean, you won't have this marginal effect in the cutoff.
Yeah, exactly. Like, obviously, well, the assumption of this regression discontinuity design is that people who are right here are very similar to people that are right here. But when we go all the way to the left end of the distribution and all the way to the right end of the distribution, there's going to be some sort of selection bias, right? Like, people who are scoring 20 probably would have never even got close to this cutoff, right? So they're going to be a lot less likely to complete college than people on the very right tail. Okay, and so people who are on this right tail, like, are super high achieving, they do really well in school, they easily got the scholarship, and they'll probably easily complete college. Whereas people right at this cutoff, they're not too different from the people who just barely didn't get the scholarship. So then when you're looking at that really tight proximity, you can see the true effect of what the scholarship is, right? So here's going to be the treatment effect plus some selection bias, I would say. I don't know if you can see that. That's going to be treatment plus selection bias over here when we look at, if we compare this whole group. Whereas if we just compare the difference in outcomes right here, that's what we need for causality. And that is based on a few assumptions, which we will talk about soon. Okay. Any questions on this beautiful drawing? So just like, I really like the term window for causality because it's helpful to think about how we can only look within a small area or window to find causality, because away from that, the further we move away from that, there's going to be more selection bias. People who get really low grades, maybe they have lower ability, they don't even care about college, all of these other factors that are going to make them really different from the high end of the scale. And so to look really narrowly into the causality is to find a group that are pretty similar. Since the basically cutoff rule of the scholarship was decided somewhat randomly, right? Okay, so I'm gonna delete that. Actually, let me share. Okay. So yeah, obviously I drew that to have a discontinuous jump in the outcome, right? So we saw at the 80% grade, you saw a jump in the probability of completing college. Obviously, I just drew that effect, so yeah, it's obviously going to be there. But it's discontinuous, right? Because it's not one smooth line. You actually see two different linear functions. So an interesting and important feature of regression discontinuity design is that there's no value of xi, which we get to observe both the treatment status, or both the treatment and control observations, right? So if you're below, in this example, if you're below 80%, you don't receive the scholarship. And if you're above 80% or equal to, you do. So we have the counterfactual problem, right? Because you can't receive the scholarship and not. So we're going to use some sort of impact evaluation to establish causality. In this case, we think regression discontinuity design is the most appropriate. So unlike the full covariate matching strategies, we're not going to learn matching because we don't have time. But if you guys have done matching, it's basically based on the treatment control comparisons when you condition on a bunch of different covariate values. However, we're not really looking at that. We're just relying on the validity that RD turns, basically, we're able to extrapolate across covariate values within the neighborhood of discontinuity, because we're assuming that within that small neighborhood of discontinuity, characteristics are very similar in terms of ability, ambition, etc. So, okay, so this figure is going to illustrate hypothetical RD scenario where the individual with xi greater than 0.5 is treated. So panel A, we have a linear relationship, whereas panel B, it's going to be nonlinear. Both cases, most importantly, there is a discontinuous jump in the relationship between the expected value of y given x and xi around the point x0. So x0 is our cutoff. So here you can see x equals 0.5 is our x0 for our cutoff. And you can see there's a positive relationship in both A and B. The only difference is that in A, you can see that the authors are fitting two linear relationships, right? So we have a linear relationship on the left-hand side and the right-hand side, whereas panel B, the fit is nonlinear. Okay, so normally, the smaller the window that you look at between your treatment and control group, so if you make your bandwidth really small, Usually a linear fit will be good, but when you have a longer panel of data, or so more x's, it's normally needed to have a nonlinear fit. So it's more about understanding your data than anything. So a big problem, actually, I don't know how much of a problem this is, but make sure that you guys don't mistake nonlinearity for discontinuity, right? So if you have like a quadratic term or function, don't just think it's automatically a discontinuity. If you don't just want to fit it for discontinuity. You need to actually know, okay, well, there's a reason that there should be a discontinuous jump. Maybe there's a cutoff rule. Sorry. High order. Jorge asked, high order polynomial is common? Yeah, I mean, so yes and no. Normally, if authors are doing a regression discontinuity design, they will include various specifications. So oftentimes, the main ones will be linear with a really small bandwidth. And so when I say bandwidth, I just mean distance away from the cutoff. And then sometimes they'll also do maybe the full length of the running variable and try and fit it with high order polynomials, so like a quadratic term. So yeah, it's a bit of both. Like they're both common, I would say. There's pros and cons to both. So we'll talk about that later. But basically, when you use more data, so a larger bandwidth, and you try and fit it with a higher order polynomial, obviously you have more data points, so you can estimate a more precise effect. However, you're also more likely to get selection bias, right? So when you have a smaller bandwidth, you're in a smaller window of comparison. You're more likely to use a linear fit, and there won't be selection bias, but then there's going to be higher standard error terms because you have less data points. So both are common, there's just pros and cons to each. Okay, so a simple model formalizes the RD design. Suppose that in addition to the assignment mechanism, potential outcomes can be described by a linear constant effects model. So for example, here we have the expected outcome, so outcome for the non-treated group, given xi is just a function of alpha plus beta xi. So that's saying that even before this treatment of the program, there's some relationship between our running variable x and our outcome variable. So then to find our treatment outcome, it's going to be a function of this expected outcome for the non-treated group plus the treatment effect. So that would lead us to the following regression, which is just our outcome variable is a function of the x, so beta xi, right? Because there's going to be some relationship oftentimes between your x variable and your outcome variable, and then plus the dummy variable for the treatment effect. Okay, so rho is the causal effect of interest, and basically the key difference between this regression and other methodologies we've looked at is that our CI, our treatment status, is not only correlated with xi, but it's actually determined by our x, right? So it's perfectly determined by what your xi is. So therefore, the regression discontinuity captures the causal effect by distinguishing nonlinear and discontinuous functions from the smooth and linear function xi. So we have some sort of discontinuous function where di is going to equal 1 when xi is greater than x0. So that's the causal effect that we're interested in. And so we need to distinguish that effect from just the smooth, oftentimes linear relationship that x has with y. So notice that the baseline outcome, y0y, is a function of our continuous variable xi. So this is normally what would result in selection bias and a standard OLS, right? it's the same, like what we talked about, how test scores are likely going to affect the probability of completing college based on ability and other factors. But this cutoff rule, this is separate and it's supposedly random where they decide to put the cutoff. So that's what's going to give us causality. So yeah, the functions of xi on your outcome variable can be nonlinear. You can have some function of xi, which, as Jorge said, can be basically some sort of quadratic function or polynomial. Okay. So yeah, just remember that as long as our f of x is continuous in a neighborhood around x0, it should be possible to estimate a model even if it's nonlinear. So there is a lot of flexibility here with the estimation strategy. So this would be an example of a regression discontinuity estimate with flexible function form. This is just a parametric estimate because we're trying to fit the relationship parametrically between, or parameterize the relationship between x and y. And we do this by including polynomial terms. So you can see here, instead of just the basic y is a function of alpha plus beta 1x plus rho di, we have all of these extra polynomial terms to try and fit the true relationship between x and y. I mean, no one would, normally when authors do this, I don't think they go higher than 4, but it just goes up to p to show that you can include a lot. Okay. So including polynomials, as we see here, can be useful because sometimes we might be concerned that we're basically interpreting a discontinuous jump when there might just be a non-linear relationship. So we can think that the effect size is larger than it actually is when we don't properly parameterize. So yeah, generally to avoid this problem, economists will look within a smaller neighborhood around the cutoff, just above and below. So that should lower concerns that we're looking at this huge nonlinear model when we're actually estimating a discontinuity jump, right? So when you look within a smaller window, you're not concerned about that as much. This is what I was just telling Jorge about. When you look within a very small neighborhood around the cutoff, then you have to address the problems of having less data. So your estimates are probably not going to be plagued with selection bias, like if you were to use a larger sample and parameterize, but you have less data, so it's going to be noisier. Oh. I mean, also, like when you look within a very small sample, you don't really have an average treatment effect. It's very localized. Okay, so that affects your external validity. So it's going to be biased towards the population average within the neighborhood of a boundary, which I don't think is a bad thing. Like I'd rather have internal validity and no selection bias than a biased estimate that has external validity, right? So you have to think of your trade-offs. So looking within a really small window, we would do non-parametrically. And so that's when actually, I'll give you guys a 10-minute break here if you want, and then we'll pick up at 7:10. Okay? Just because I can go on forever right now. So take your 10 minutes now and we'll, yes. Any questions before the break? Okay. Stop it. What the heck? Oh. Okay, here we go. Now I'm cooking with gas. Okay, break time. Smiley face. Or Okay. Shall we begin? De nuevo. Okay, so I had a good question during the break from Diana. So the question was basically when to prefer using a polynomial specification versus a linear model. And honestly, like there is some, I don't know, like authors do use both, but the important thing is to look at your data and the way it's distributed and to play with both functions. And it should kind of, you should be able to tell whether it's fit better to a linear model or to a nonlinear model. But more importantly than the comparison between those two, I think, is that authors are really moving toward keeping a linear specification, but then changing the optimal bandwidth size, okay? So instead of debating between, oh, how many polynomials should I use? The conversation is now more about, oh, well, how big should my bandwidth be? How many sample units should I include in my analysis to obtain causality? And so in Stata, the common one would be like by Kalanico et al., like CCT, I think they're called. Those are their last names abbreviated. And so they use RD plot, and also there's a specification to find an optimal bandwidth. I'd have to go look at it and see what it is. But that's more of the conversation for when you're looking at obtaining causality within RD. It's less about whether you should use nonlinear or linear. It's more about, okay, we'll just stick to linear and find the optimal bandwidth to remove selection bias. Okay, so this non-parametric estimation is precisely what that's doing. So we're not interested in parameterizing the whole relationship between X and Y. Why are we not interested in finding the parameterized relationship between X and Y? Well, if we look within a really small window around the cutoff, we don't need to fit everything. We can just say, oh, that's linear because we're super close in this window. So that's the strategy of non-parametric, and it's definitely been a lot more popular among economists recently. I can send some papers if you guys are interested. And so the main strategy is that instead of fitting our data using polynomials for all of X, for all of our running variable, we can just focus on data within a neighborhood around the discontinuity. So say that's the interval, the cutoff, x0 minus delta and x0 plus delta for some arbitrarily small number delta. So delta is just this really small number. Obviously it's not precise, but that's part of the bandwidth optimality that we're going to be choosing when you actually work with your data. So the delta will depend on your own data set. So that's why we don't give you a specific number, right? So each data set is unique, like a little snowflake. So you can't just say delta is 20 or whatever, because all running variables are going to be different and contain more data points and might require more or less of a range. Okay, so then we can say the following. So the expected value of our y for xi less than x0, so our individual I is characteristic less than the cutoff, but still greater than x0 minus delta, is basically the same as the expected value of y when xi equals x0 precisely. And then the same for the other group, so the expected value of y, given that our xi is above the cutoff, but below x0 plus delta, is approximately the same as the expected outcome given xi precisely equals our cutoff. So what's that saying? Basically, we're saying that when you're within this delta, so you can see we have a window from x0 minus delta to x0 plus delta. So comparing the average outcomes in a small enough neighborhood to the left and to the right of x0 should provide an estimate of the treatment effect that does not depend on the correct specification of a model for the expected value of y given x. So we're basically saying that when we're close enough within our delta range, our expected outcomes at baseline will be the same between treatment and control group. So we're saying they're basically identical. Are there any questions about this notation? Okay, just look it over. I mean, it might look confusing, but it's pretty intuitive. We're just defining some window around our cutoff, the size of delta on either side. So we'll have x minus delta and x plus delta will be the two cutoffs of our window, and we'll only look within there for analysis. And so we're comparing the individuals who are below the cutoff and above the cutoff to each other. And we're saying they're basically identical because their yi's are basically the same. Jorge, you need a lot of observations near the cutoff. That's true. We definitely prefer that because obviously the more data we have, the better. So you want a lot of concentration in data so that you actually have a sufficient data size in your treatment and control group. So that is very important. If you only have like 5 people within a window on either side, you're obviously not going to have enough power. So when you consider a regression discontinuity strategy, you do need to think about power and how much of the sample. Nicholas says, is there a specific percentage required from this full sample? No, there's never been like a percentage requirement. But I mean, you do want to consider power. When I've had experience with regression discontinuity for a paper with Marcos, and basically the optimal bandwidth was decided by the CCT calculator. I think it's like, I have to go check my code, but it's like optimal bandwidth or RD bandwidth or something like that. I know RD plot will actually create the plot, but I'll check that out. And so that will basically choose the optimal sample size based on the error terms and the amount of, I can't quite remember the formula. I'll have to get back to you. But there's never a specific percentage required, no. It's more of like a power function, yeah. It's like how to like optimize power. So yeah, something like that. I have to check it out. But definitely, you guys, if you have questions on this, I'll send you the paper, but it's like CCT Delonico. And then just like those authors and then optimal bandwidth selection is basically the whole conversation on how to choose the correct sample size for validity for a non-parametric estimation. Okay, so generally when we use a non-parametric estimation, thanks, no problem. I don't know if I was actually helpful, but at least I pointed you in the right direction. So yeah, the general specification, which I showed Nicholas at the beginning of class, takes the following form for a non-parametric. And if you guys think about it, it's kind of similar to a difference in differences, because the only difference is that instead of a time dummy, we're using distance from a cutoff, right? So you have your treatment, you have your basically second dummy, and then you'll have an interaction of the two. So that's the same kind of setup for difference and difference, and it definitely helps me remember the specification. So yeah, to explain our outcome variable, you have a dummy for treatment, so equals to 1 if you're on the treatment group, plus beta, which is the distance between individual eyes running variable and the cutoff score, and then an interaction of the distance variable and the dummy. So the idea of focusing on observations near the cutoff value, so the discontinuity sample only, gives us valuable robustness check, just because although RD estimates are going to be less precise as we have a smaller window, the number of polynomial terms needed to fit the function of xi will go down for sure. So hopefully as you zero in on x0 with fewer and fewer controls, the estimate effects of DI will remain stable. So if you guys want to do some sort of robustness to your RD analysis, you can always start from maybe your full sample of xi. So let's say we're looking at the test score example. So we use everyone's test scores and every individual, whether they scored 0 to 100, and we try and fit it polynomially. And then we can start reducing the sample size and maybe fit it less using a linear model or whatever form. And hopefully you'll have some precision in your estimates between the different models. If not, normally you would trust the ones that have a smaller window. You would say that normally the larger sample would probably contain selection bias. But this is more of an old method of doing RD. So just basically randomly choosing bandwidth specifications and checking for robustness. Definitely the more recommended way is to follow the Colonico optimization formula, which is nicely packaged in Stata. What does the number of polynomial terms imply? It's just it's the difference between the parametric and non-parametric fit. So the parametric fit is when we're using polynomial terms. Obviously, there's going to be some relationship between our outcome variable and our running variable. So it might be linear, it might be nonlinear. So the more polynomials you add is just trying to better fit the nonlinear function, right? So as we move in to a smaller window of data, we often need less polynomial terms just because there's more likely to be a linear fit when you're looking within such a small window. Whereas when there's a large window of our test scores, there might be a nonlinear relationship between test scores and the outcome. That's basically the reason. But you don't see too many overly fitted regression discontinuity designs anymore. The highest polynomial would be like of order 4 that I've seen. So yeah, but that's just the goal, is to fit properly the relationship between x and y. And the reasoning for that is because you don't want to mistake just a nonlinear relationship between your outcome variable and your running variable for a discontinuous jump. So you want to make sure that you're parameterizing if the function really is nonlinear. No problem. Okay. So that's the function for non-parametric. Remember how the parametric function, we had all of those polynomials, so that's basically the difference. This would be typically using a larger data set within our sample, and then this would be much smaller. So this may be, for example, the parametric estimation, we would contain the whole test individuals with any test score, so from 0 to 100, whereas here we might really narrow it down, so between, I don't know, like if the cutoff is 80, maybe from like 75 to 85. So another important thing to check is that the pre-treatment variables are unaffected by treatment or any other characteristics really. Basically, we want to know that the only thing affected by this program is the outcome variable of interest. So we don't want characteristics to have a discontinuous jump across the threshold. We don't want, well, we don't want pre-treatment test scores to be affected by the outcome, but that doesn't really make sense in this application. So the biggest factor would be like characteristics, so age or sex or test scores for maybe another type of exam. Would that be considered placebo tests? Yeah, I would say that's maybe like the thing about placebo tests is we're often trying to check for a fake effect. So I would more say it's like a verification of the causality of the analysis, right? Because if we're saying that the only thing that changes continuously across the threshold should be the outcome, then we can verify that by showing that all of these other characteristics don't change, so that we have some sort of basically continuity between the two treatment and control groups. So I wouldn't quite call it a placebo, but pretty close. More just confirming your identifying assumptions. No problem. Okay, so let's talk about the assumptions needed for regression discontinuity design. So these are the requirements that we have to have for causality. There's definitely more than some of the other models. So here they are. So the first one is that the cutoff must rank people in a continuous or smooth way. So it has to be a continuous variable. So for example, poverty scores, test scores, or age have very many values that can be ordered from small to large and can be therefore considered smooth. By contrast, variables that have discrete categories can only have a few possible values so that people get ranked into and therefore they're not smooth. That could be like employment status, so being employed or not employed, highest education level achieved, country of birth. These are categorical variables and they won't work for a regression discontinuity design. Because remember that we had to, for causality, you need to arbitrarily say, okay, 80% is the test score we need for people to receive the program, right? So when it's really discrete categories, then you don't have that smoothness or continuity. And there's more likely to be differences in characteristics between people in the treated group and people in the control groups, right? So yeah, for example, highest education level achieved, what would be like the possible, like if highest education level would be like primary, secondary, like university or college, master's, PhD, you can see how those are pretty wide categories. And so a lot of things can be different between someone who just completed high school compared to someone who has completed university, right? So you can see how that wouldn't satisfy the demands of regression discontinuity design because we need to have some sort of random cutoff and compare people right around the cutoff. So there's no one right around the cutoff of like graduating high school, right? Because then you'd be comparing people who graduated high school to people who graduated only secondary. And you can think how those two groups would be very different. So yeah, there's a lot of problems with comparing between discrete. I think some authors have tried it and talked about the methodology. It might be on my reading list, so I'll post it on SIGA. I don't know if we'll have time to read through it. Okay, so the second requirement is there must be a clearly defined cutoff score. So a point on the index above or below which the population is classified as eligible, right? So that's pretty obvious, I think. Like if we're going to know who's treated or not, we need to have a clear definition of who is eligible for the program. That's obvious. And then the next one is that the cutoff must be unique to the program of interest. So there should be no other program apart from the program to be evaluated that uses the same cutoff scores. Why do you guys think this is important? Oh, everyone's leaving me. Why do you guys think the third requirement would be important for causality? Confounding? Yes, I love the buzzword. It is confounding because you're going to basically not be able to separate the true treatment effect that you're interested in with the other program that the same treatment group will also be eligible for, right? So you can't have exactly the same cutoff score. Okay, so that's the third requirement. So we need to have a unique cutoff score. Our basically running variable, or our x, must be continuous, and we must precisely know what the cutoff is. So we know who's in the treatment group and who's in the control. And finally, the score of a particular individual or unit cannot be manipulated by enumerators, the benefits of the program, administrators, politicians, and that's called no bunching. I'm not sure if you guys have heard this in previous courses where you've covered regression discontinuity design, but what do you think would be the problem if people could manipulate what their score on an index was? Endogeneity would arise. True. Yeah, endogeneity, because, well, people would be able to choose whether they receive treatment or not, right? So if someone who is in the control group can somehow manipulate their scores to say that they should be treated, then they're going to be selecting themselves into the treatment group. And so we'll have that whole self-selection problem, which is the same as the problem that we talked about in randomization with imperfect compliance, right? So manipulation of the cutoff or around the cutoff is really dangerous to the validity because just because, yeah, selection bias. Okay. So, okay, so yeah, manipulation is very important because that would harm our estimates. I think I'll show you what it looks like too. So I think I said this already, but the causal inference of RD design will be the impact around the eligibility cutoff as the difference between the average outcomes for humans on the treated side of the eligibility cutoff and the untreated side, right? So you have the discontinuous jump, so you're just comparing the distance between the 2 points. Okay, so let's consider an example. Sorry. Oh, was my screen not sharing? I'm sorry. Can you see my screen? Sorry. Yes.
No, it's wait, the PPT, the PowerPoint, the presentation.
Yeah. Okay, good. Thank you. Thank you all. Sorry. I'm a scatterbrain right now. Okay, so let's consider an example. So suppose that there's an agricultural program that aims to improve total rice yields by subsidizing farmers purchasing fertilizer. So they want to target small and medium-sized firms. So they're classifying these farms as fewer than 50 hectares of land. So before the program starts, we might expect smaller firms to have lower output than larger firms, right? Economies of scale, maybe larger firms are more efficient, so they can produce more. So we really don't want to compare small firms to large firms because that would create omitted variable bias, right? Large firms are more efficient to begin with and they can produce more. So basically what the RD wants to do is calculate the difference in outcomes, which would be rice yield, on either side of the eligibility cutoff, which is having a farm size of 50 hectares, right? So any farm under 50 hectares will receive this program. So farms that were just too large to enroll in the program are going to be the comparison group and generate the estimate of the counterfactual for those in the treatment group who are just small enough to enroll. So like maybe like 49 hectares to 51, something like that. So given these two groups of farms are very similar at baseline, I'm just assuming this, but you can always verify that with your sample of data, right? So you never need to say, oh, well, we assume these two groups look alike. No, you can show it because you're going to have data on characteristics and incomes and farm behaviors, for example. So you always want to show that your groups are similar. You should have data on that. I'm pretty confident that you would. And then you can also assume that they're exposed to the same set of external factors over time, such as weather shocks, price, local and national agricultural policies. You're gonna want to use a more localized data set for those assumptions. So if you have those two, then the only real reason for any difference in outcomes must then be the program itself. Okay, so a note about external validity. Since the comparison group is made up of farms just above the eligibility threshold, the impact given by an RD is only valid locally. So this is the average treatment effect within the small neighborhood of the eligibility cutoff. So we can't use these estimates of a regression discontinuity design to say it's an average treatment effect for the whole population, because it's not. We can only make inference for the sample size that we're looking at because it's very specific. And yeah, they might be a lot different from really large farms or very small ones, right? So this is a very important distinction of a regression discontinuity design to other methodologies. Okay, so also a key component of this example is that we wouldn't really, oh, that's just what I said. Okay, so I just said here that the impact evaluation, we won't be able to identify the impact of the program on the smallest farms, so those with 10 or 20 acres, or for really large ones. So we'll only be able to really make inference for the same size farms that are in our sample size. Okay, so this is the treatment effect. This will always be like your regression discontinuity graph if you're doing this type of analysis. So you can see that they're doing a linear fit here. And so they estimate two linear regressions, right? One on the left-hand side of the cutoff and one on the right-hand side. And you can see A minus B is the impact of interest, but only for within our window, our causality window. So it's likely not for the whole sample. It's more normally around just the small cutoff. So yeah, that's a very simple analysis, right? The difference between the two lines is the causality. And you can see they do have a lot of data points concentrated in this middle area, so around the cutoff, which is really great. And there's less data points at the extremities, which I would say is pretty typical too. You don't expect there to be many data points at the extreme values. Okay. Okay, so fuzzy regression discontinuity design, I'm not sure if you guys have covered, but it's basically facing the challenge that sometimes units do not respect their assignment to the treatment or comparison group. So it's the exact same situation as imperfect compliance in randomization. Just this time we're using the regression discontinuity design. In other words, some units that qualify for the program on the basis of their eligibility index may opt to not participate, while some units that did not qualify might find a way to participate. So then we're going to use fuzzy RD. So we say when all the units comply with their assignment, that means we're gonna use an RD. That's sharp, so a sharp RD. And then when there's non-compliance on either side of the two cutoff, it can be just one-sided or it can be two-sided non-compliance, then we're going to use a fuzzy RD. So this is using the instrument variable approach, which we saw in chapter 4. So this is just graphically showing the difference between a sharp RD and a fuzzy RD. So you can see here, remember that we talked about a sharp RD being completely deterministic for treatment status, right? Once you know what the XI is, whether it's greater or less than the cutoff, you know exactly what the treatment status is, right? So in picture A, you can see how when your XI is less than 50, everyone is treated. And then when XI is greater than 50, no one is. On the other hand, for a fuzzy RD, it's not completely deterministic because there's going to be some probability of being treated based on the cutoff score. So you can see when individuals have an XI less than 50, they're more likely to be treated than when they're above 50. So there is a higher probability based on the cutoff score, but it's not fully deterministic. There's going to be some increase in probability. So that's the important difference between a sharp RD and a fuzzy RD. Okay, so we're out of time, so we will continue this, I think on Monday. I need to email Vadim. I think you guys will have a guest lecture on Wednesday. I will send an email tomorrow if that's true, okay? So if it is, I would like you guys to come because he's going to be working with us on R. I think it'd be really helpful for you guys, especially if you're interested in doing anything with predictions or machine learning, etc. It will be very cool. So yeah, if there's no questions about any of the topics or the referee report, you guys can have a good night and I'll see you on Wednesday. Okay, are the slides on SIGA? For the last guest lecture, or this one? This one. Yeah, they should be there. Yeah, they're there. I'll double check, but I think they are. No problem. Okay, bye guys. Have a good night.